Welcome to the 6th Elsiveer Distinguished Lecture in Mechanics. Today I am pleased to introduce our speaker, Professor James Rice, who is the Mallinckrodt Professor of Engineering and Science and Geophysics at Harvard University. Professor Rice was previously a member of the faculty at Brown University till 1981. He was educated in engineering and science and applied mechanics at Lehigh University. Professor Rice has made seminal contributions to many fields of mechanics, including crack propagation of elastic materials, plastic materials, inelastic constitutive relations for solids, wave effects in tensile crack dynamics, thermodynamics of interfacial embrittlement, and computational mechanics. In recent years, he has focused on mechanics directed to earthquake and environmental problems, including fault zone processes, earthquake nucleation, dynamic rupture propagation, meltwater interactions, landslide processes, and general hydrologic phenomena involving fluid interactions in deformation, flow, and failure of earth materials. His presentation today concerns material physics of fault processes in rapid shear and consequences for earthquake dynamics. I'm pleased to present him to you today. Please join me in welcoming Professor Rice.
Thank you all for coming. It's been just a lovely visit so far. Now I have to do my part of the talking. So you see the topic, and the work I'll describe is mostly with collaborators who are listed here, and I'll try to mention who as we go through different things. So what drives the work I'm going to discuss today is the quandary in seismology of long-standing, which is illustrated here. And that is when you look at typical lab values of static friction coefficients, at least for rocks, they are high, of order 0.6 to 0.8. And I'll remind you that the static friction coefficient enters in an expression for the shear strength of a contact, like the surface of a fault. The shear strength is the friction coefficient times what's called the effective normal stress, the total stress clamping the fault shut, minus the pressure in any infiltrating pore fluid. And as fault zones are ground up granular and hence porous material in the earth, our default assumption always is that there's fluid infiltration of any pore space. So we have to worry about this term, and as I'll explain, it becomes very important, the pore pressure, for dynamic weakening mechanisms. So that's fact number one. The static friction coefficients, at least, are quite high. Fault slip zones on mature faults are, in fact, astonishingly thin. It looks like most of the slip is taken up on regions whose thickness is of the order of a tenth to a few millimeters, despite the fact that the fault zone itself has damaged, highly cracked material extending over distances from meters to a kilometer about the fault. Wider distances for more mature faults, and by more mature faults I mean a highly slipped fault, one that has, through say hundreds of thousands of earthquakes, slipped many meters in its life, many kilometers I should say in its life. Well, the quandary is this: if those friction coefficients prevail during seismic slip, there should be an enormous amount of heat outflow. And the heat outflow itself should be limited by the fault zone melting. So when we look at faults that have participated in earthquakes, we ought to find evidence that there was previous melting. And while occasional signs of melt, typically from faults that are thought to have been active at depths of order 10 or more kilometers, such things are found, the basic thing is that in general we don't find either of these. So that's the quandary. Our most direct expectations from lab measurements of friction and from what we know about how thin the zones that take up a lot of slip is, these are the things that should happen, should be observable, and they are not. Now, just to emphasize the thinness of fault zones, to go back to that, here's a picture of most of California, or at least the more southern part. And this box corresponds to the big box that you see here. We're seeing here the San Andreas fault, plus a number of other faults of that same system. And the next picture I'm going to show you is data from the Punch Bowl fault. That's this fault right here that I'm focusing on. And it's a fault which is now extinct, but in its lifetime was thought to have slipped on the order of 35 or so kilometers. So that would mean just thousands of earthquakes if you think of each earthquake giving you slips, say, of order 5 meters or so. And this was one of 2 observations published in the same year, which changed the way everybody in this community thought about the earthquake process. So here we're looking with a 0.1 meter scale bar at an exposed section of that fault. The people who did this work, identified here, had to carefully clean off that surface, remove all vegetation that had grown on it to expose this. But what was a great surprise to them and everyone else in the community is, look at these black arrows. They mark a very thin zone, and as far as they could tell, essentially all of the slip, kilometers of slip, were confined to that very thin zone. To see how thin it is, we look at a so-called thin section study in polarized light of a section cut out from around here. And now that's a 5 millimeter scale bar. And what you see is a highly altered zone, which is thought to be the location of shear in the individual earthquakes. And it has a thickness which, depending on where you measure for this darker part that actually is the shear zone inside, it has a thickness on the order of 100 to 300 microns. So this was, as I said, an astounding observation, which was very hard for people to accept simply because they're used to thinking of faults as broad zones of granulation and damage, and yet there's this extreme localization. That's something which we try, by the way, to explain in our work. Now, the fault gouge, this ground-up material from previous earthquakes, is, after all, a granular material, but it has a very strange size distribution. Here, in looking at 2-dimensional cross-sections of samples of that fault gouge material and using either for the smaller size range transmission electron microscopy or direct optical microscopy, you're looking at the number of particles per unit area that you find in particular ranges of particle size. And what you have is this distribution which has the number going in proportion to particle size to the -2 power. It's a distribution which could not continue indefinitely because it would overfill space. You can't integrate up that kind of density of particles, integrating with respect to particle size, and get a convergent integral. So it has to be cut off, but the data itself seems to go down to some tens of nanometers. It looks like my laser pointer is giving up on me. But the data goes down to some tens of nanometers and up to a few tens of microns. So that's the arrangement. It's this, as I said, quite strange distribution, though we've since seen that other natural shear zones tend to have comparable distributions. Those are from volcanic plugs, sort of round blocks of rock that have been forced up the caldera of volcanoes from building up of magma pressure below, so you have a highly sheared zone at their edge. And another source of data which shows size distribution somewhat like this are from the beds of mountain glaciers where rock has been abraded by the sliding ice. So it seems to have some generality. Now, the difficulty is that if we try to appeal to classical granular materials ideas, we usually think of shear zones as running from 5 to 10 particle diameters, and it's not clear what should be meant by particle diameter here. My telephone is ringing if you hear music in the background. It's not clear what should be meant by particle diameter, but if we take D50, the size where 50% of the mass has particles of greater size and 50% less, then that would suggest shear zones of 5 to 10 microns. But the trouble is we have lots of particles that are much bigger than 5 to 10 microns. So it's not clear even how to use these classical guidelines from the granular materials literature. Okay, now as I said, there were two discoveries published in that same year which changed perspectives. The other was from a large earthquake in Taiwan that occurred in 1999, a magnitude 7.6, the so-called Chi-Chi earthquake. And there people drilled down to intersect the slip surface of that earthquake. This is an example of a core that has traversed the slip surface. And what you see, again, there's a 0.1 millimeter scale bar, so you see an extremely thin zone. The investigators suggested 50 to 300 microns thick. Other penetrations of that fault, these some years later, one of them again suggested a rather thin zone, but now about 3 millimeters thick. Yet another, though, suggested thicknesses that are still small, but still an order of magnitude or more bigger, a couple of centimeters thick. But thin in all cases, but whether it gets thin like 100 microns is not clear. Now, this is put up for two reasons. First, it's another fault zone, the median tectonic line fault, which runs across the principal islands of Japan. And it's a hand-sketched view on a funny logarithmic scale, but it shows a similar idea, and there is a central slip zone, which again is thin, of the order of 3 millimeters wide. This is up here for another reason, though. Whenever we have to have numbers for parameters that enter simple theoretical models, what we resort to is data from this fault zone. And here there are lovely studies where the permeability of the rock, resistance to fluid permeation through it, is plotted as a function of distance from the fault for samples which are confined. These would be round samples which would have equal stresses in the transverse directions and a comparable one in the vertical direction of 100 MPa here, but at different levels here. And look at 50 MPa data, where you read the permeability up here. And what this indicates, two curves, is it depends on whether you got to 50 MPa by first, for example, compressing to 200 MPa and then unloading, or whether you got to 50 MPa by just the original load rise. So it's irreversible, and anyone who's looked at the loading of soil materials will understand that kind of consolidation behavior. Permeability, by the way, is the quantity which gives you the mass of fluid crossing unit area in a porous medium in terms of the viscosity of the fluid and the gradient in pore pressure within it, corrected by gravity. That's called Darcy's law, if you have not encountered that. Okay, so that means that we do have some sources of data to put in our models. So how do we explain these apparently weak faults that don't generate the heat that we would expect them to generate? And one line of explanations, which has an old history, are just to say fault materials are different. They're made up of things with very low friction coefficients. And there are indeed often found clays among the minerals in fault zones. So we can't dismiss this. It's becoming more and more unlikely, I think. But that's a possibility. Another possibility is maybe the friction coefficient isn't low, but pore pressure is a lot higher than we think. When we make elementary estimates, we usually assume that the pore pressure varies hydrostatically with depth, as if you had dug a well deeply into the earth and just let it fill naturally with groundwater. But that need not be the case, and there are scenarios of high pressure. But what my group has been working on with that cast of characters that you saw listed at the beginning is another way of looking at this problem, and that is to say, well, maybe faults really are statically strong, but they're dynamically weak. And that's because things happen to them as they start to shear and start to get hot. And there's almost a laundry list of processes. I'm going to spend some time on principally thermal pressurization and thermal decomposition, but it is a longer list. So let's go through what some of these are. So first, I'm going to skip quickly through some slides on flash heating, but one of the issues is even when you have bare rock on rock in sliding, even though you have a very high friction coefficient, when you slide fast, the friction strength diminishes a lot. And the basic physics is easy to understand. True friction, as Bowden and Tabor pointed out in the middle 1900s, true friction resistance comes from something approaching true atomic scale contact at isolated asperities. So whatever the macroscopic stresses are that you apply, the local stresses at these contacts, which carry all the load, are far, far greater. In fact, it's thought that the normal contact strength is very close to the theoretical strength to plastically indent even a ceramic material like a rock. So the shear stress is indirectly inferred to be very high too, of the order of 1/10 of the elastic shear modulus. So these are enormous stresses. That means that as we slide, we generate a lot of heat. And if we slide fast, that heat does not have time to diffuse away, which means the temperature goes up. So there's an elementary model of this process, which just imagines that you get the contact hot enough to weaken. Now, weaken can mean different things. In some cases, it means you're forming perhaps a few nanometer layers of melt here. In other cases, you're simply inducing unstable minerals to thermally decompose because they get hot enough. But the idea here is that there's a certain critical velocity, and if you slide any faster than that, you get into this range where the friction becomes dramatically weak just because the asperities aren't strong. And that simple model, and again, I'm not going to work you through this other than to point out, it does give plausible fits to data which is, in this case, very highly scattered, but this shows that when you slide faster than a number of around 0.2 meters a second, in this case, 0.14 is a better fit, you do have a dramatic fall off from static friction, which you get at lower rates. Also, tests like this is called a split Hopkinson bar or a Kolsky bar. And in experiments like this, my device seems to need a rest again. But in experiments like this, if you look at the curve labeled coefficient of friction and you measure that on the left side, oh, thanks very much. Okay. If you look at the curve labeled coefficient of friction, you see that the friction in this experiment, which involved much higher slip rates of the order of 4 or so meters a second. So these are slip rates that are really of interest for earthquakes, in contrast to those in the experiment I showed you on the previous slide. At these slip rates, the coefficient of friction is really low. It never gets above 0.2, whereas static friction was up here close to 0.7. By the way, this data cannot be believed beyond that dashed line because the wall of the specimen cracked. So the experimentalists were probably too ambitious in terms of the normal stress that they ran this experiment at, but they were trying to avoid another typical criticism of lab tests, that normally they're run at very low normal stresses, far away from what you see on a natural fault, and they wanted to get up to reasonable values there, which they did. Okay, So let's go into this business of thermal pressurization, one of the two classes of mechanisms of dynamic weakening that I'll spend some time on. So just think of a fluid-saturated layer of gouge material, and imagine the more coherent walls are being sheared at a certain velocity v in an earthquake. We have a normal stress, and we would typically want to think of the fault zone and sometimes its surroundings as permeable and hence what we call poroelastic. For the fault zone, perhaps poroelastic plastic would be a better word. So we're shearing this. Typical rates of slip in an earthquake are on average of the order a meter a second. They could be an order of magnitude higher near the propagating tip of the crack-like rupture that an earthquake represents. But we've typically, when we need numbers, use a meter a second as an average velocity here. So these are the set of equations you could set up. First, if the layer is quite thin, we can forget the right-hand side of the equations of motion. And if we assume things only vary with distance through the layer, this says the shear and the normal stress are spatially uniform through the layer, though of course we fix the normal stress, but the shear stress in our solution will vary with time, but it can't vary with distance across the layer. We have an energy equation, which is in its simplest form as this. So this is the rate of temperature rise, which is a rate at which the material takes up internal energy. Why does it take up internal energy? Because it's being heated, but some of the heat flows away by heat conduction, which is the origin of this term here. The alpha thermal is the thermal conductivity, and that's typically thermal diffusivity, I should say, is typically of the order of a square millimeter a second. There are other things that enter a proper energy equation, but you can look backwards at solutions you get and see that they make small contributions as the fluid within that zone heats up. It wants to get out of there. There's a flow out, but the advective transport of heat in that flow is rather small, so we don't bother with it. There's also an equation for conservation of fluid mass. So one effect here is as the temperature rises because of the frictional heating, the pore fluid, if it can't get out of the pore spaces, has to see a rise in its pressure. Lambda tells you how big that effect is. But the pore fluid can diffuse. It's in a deforming porous medium. So there's a Biot-Terzaghi-like diffusion process that goes on, which has the diffusivity alpha hydraulic. And what we also do is, in order to deal with the situation that we're imagining a material resistant to localization, we make, at least for small perturbations from uniform shear rate in the layer, we make the material rate strengthening. That makes sense, A, because a lot of materials are rate strengthening when we look at lab results on them, and B, if they are not rate strengthening, they become so as their temperature rises. And I should also say C, if they were permanently rate weakening, the game would be over. We would have no trouble understanding why shear would localize to an arbitrarily thin zone. So we focus on rate strengthening friction as something that fights against the localization that's otherwise inherent in those equations. A measure of how strong that rate strengthening is for other reasons given the label A minus B. That has to do with the larger literature on friction. So here's the first thing that was done by Lockenbrook many years ago. He imagined such a layer was between two half spaces that he regarded as impermeable to fluid flow and adiabatic, non-conducting, and worked out a solution where there was homogeneous strain within the layer, a velocity distribution through it that looks like what you see here. And he got this exponential weakening. So the shear strength, which given by the effective stress idea. Because the pore pressure rises as the stuff is heated. The basic idea of this mechanism is that as you get a mixture of water and rock hot, the rock wants to expand thermally a little bit, but the water wants to expand thermally, let's say, of order 50 times more. Well, the water is locked, though, in this very tight pore space. Remember, the particle sizes of this gouge are quite small, so it's a very low permeability material. So the only possible response is that the water shoots up to a much higher pore pressure. Anyone ever do ceramics and put your ceramics in an oven? Yeah, okay, so ceramics are clay. When you mold your ceramic, it's full of water, so think of it as like fault gouge. When you put it into an oven, you bring up the heat very slowly, because you know if you bring the heat up fast, you'll build up big pore pressures and you'll crack your beautiful ceramic vase. So it's the same idea here but we have big stresses from the rest of the earth to avoid cracking, but we do frictionally weaken the material. So what we found, however, is that this solution is not a stable one. And in particular, by looking at the perturbed response of that system of equations to small perturbations about this uniform flow, we can figure out a critical wavelength, and what's more interesting is sort of like a half wavelength, because that's what you could fit into a zone like that, which is given by this expression. Basically, it gets its physical dimensions from diffusivities divided by shearing velocity, which has units of length. So that's where the length comes from. This is non-dimensional, and so is this in front. So if the homogeneous shear is unstable, that suggests that it might localize into a narrow zone. So this led us to make elementary estimates of the localization widths that you see here. So this repeats a formula from the previous slide. So what we've assumed is a velocity of a meter a second, representative values for this measure of friction divided by rate sensitivity of friction, somewhat low friction coefficient, so things scale with 1 over the friction coefficient here. Diffusivities thought reasonable, and from the direct experimental data on the median tectonic line gouge, but at pressures corresponding to about 7 kilometers depth, what we get are localized zones which are of the order of 10 microns or so. You could put large factors on that final number because there's a lot of uncertainty here, but at least we get extremely thin localized zones predicted, or I should say hinted at, because this is still linear stability theory only, and we're looking at the first wavelengths to go unstable, but they're very small wavelengths. This is a half of wavelength. And another estimate, though, is to say, wait a minute, in the real Earth, when you have an earthquake, you have this crack-like slip process that is propagating along the fault. It concentrates stress ahead of it, and it must broadly damage the material. So before the material sees very large shear, it sees these big concentrated stresses. So we've also always tried to do estimates of, though the adjustments of parameters are somewhat arbitrary, but try to represent the effect of fresh damage. And for numbers that I think are probably more or less plausible, that could increase this by a factor of 4 or so. So that's the range that we would expect based on just linear stability theory. I should also mention there's something really curious about the linear stability theory here. We actually have a set of linear perturbation equations. So we want the time dependence of each coefficient of a trigonometric term in y. That set of equations has a time-dependent coefficient, because we're perturbing about a base solution which is not steady, but which has that slow exponential weakening in it. So it happens to be a system where you can write down the exact solution for the time-dependent linear perturbation equations. But because of that time dependence, you have something mathematically that's curious, but it's certainly what the equations imply. And that is the following. If you go to wavelengths just slightly longer than that critical wavelength, for which I've given you a formula for, if you go to just slightly longer wavelengths, you have the situation where the perturbation of strain rate grows exponentially in time, but the perturbations of pore pressure and temperature decay exponentially in time. So it's really a very bizarre kind of transition, but it's what is implied. Well, this was just to show us that, let me do this first. Okay. Oh, I should be on okay. So let's, no? Cancel. Okay. I use a Mac, so I don't know really what button to push here. Oh, okay. Whatever button it was, that seemed to work. Yeah, this is just to show you that in real experiments, we can see this process of thermal pressurization. This was actually from gouge from that same punch bowl fault that was disaggregated, put into a rotary shear apparatus. And you can see that the pore fluid, the center of the apparatus is here, so the highly sheared part is out here near the edges. And you can see that the material underwent a transition due to high pressurization. Here, unlike in the natural situation in this experiment, the water is well below its critical point conditions, so it flashes into steam. That's why it fluffs up the gouge. That would not happen at typical seismogenic depths when you're at pressures above the critical point pressure. And finally, within that fluffed up, thermally pressurized gouge, you develop a real localization, which is a few tens of microns in width. So that looks something like it. So now we decided to spend some time on full nonlinear solutions, and this part is mainly the work of my graduate student, John Platt. It's listed here. And so first, previous stuff I showed you was linearized perturbations of this configuration. Now we just grind through the numerical solution, putting in a small perturbation of a certain wavelength. And the thickness of the shearing zone is 5 millimeters in this particular set of simulations that you see. But the final strain rate after this system settles down into a highly localized state is given by that blue bell-shaped curve. It is actually rather well fit by a Gaussian, but here on this slide it's fit by a rectangle of equivalent area. So what you see is even though we start shearing a zone 5 millimeters thick, all of that shear ends up concentrated in the zone which is, of the order of 50 microns wide. So that's, what is 50 microns over 5 millimeters? That's like a tenth. Yes, that's a, sorry, I'm not doing the math very well. Help me out. But that's a small fraction of the overall thickness of the zone. So this shows that the nonlinear solutions really do have strong localization. This is just some stuff to show the dependence on thickness of the zone. Obviously, if we make the shearing zone too thin compared to what we expect to be the range of unstable wavelengths, then you're not going to have a localization, but if you make it thick enough, you do, and then the localization thickness is not strongly dependent on how wide you make the zone. Here, 10 to the 4th microns would be a 10 millimeter wide or 1 centimeter wide zone that's shearing. Now, other things you see is that when this instability develops, especially when it develops in wider zones, well, what you see here is if you deform this wider zone, uniformly you would have the exponential weakening. But as we've seen, that's an unstable solution, and what the nonlinear analysis picks out is this really incredibly dramatic weakening that sets in once the average shear strain in the zone is somewhat above 2. Because the zone is 5 millimeters thick, that would mean 10 millimeters slip. So we're talking about a healthy amount of slip. You could feel an earthquake if you were within 10 kilometers of it, which had that much slip on it, though it wouldn't be likely to do a lot of damage. On the other hand, if you start with a much thinner zone, you still get a dramatic weakening, but it's less, fractionally less of a departure. Now, there are other processes that can set in at large enough slip. So I've separated these two that I talked a little bit about the first and a lot about the second, because they're things that we think are generic. They should happen in virtually all fault zones in the crusts, unless somehow the fault zone is totally sealed off from any ground fluids. On the other hand, there are some other things that can take place before we get to really high temperatures, and by really high temperatures, I mean those big enough to melt. So it's related to the things that can happen which actually avoid melt in many earthquakes. As I said, we don't see signs of melt. So the first one is thermal decomposition. And here the idea is that fault zones typically have thermally unstable components. They have clays. A clay is a mineral with a lot of water in its structure. If you get this very hot, the water wants to go out, and you tend to develop a more coherent mineral. Carbonate rocks are similar. They will decompose into CO2 and some denser phase of rock. So these are the kinds of decompositions, and carbonates and clays and phyllosilicates is a more general term that includes clay, serpentines, and the like, are fairly common constituents of fault zones. So here I just give you the chemistry, and I was a terrible student in chemistry, and I can't swear anything about this, and I'll blame most of this on my collaborators, especially Nicholas Brontë, but these are typical reactions that are expected in dolomites. So these would be carbonate rocks that would release CO2 at high pressure. And there are two main reactions here. And then in clays and hydrosilicates, this is the work of Nicholas Brontë, at temperatures around, well, over a range around 500, 300, 800 in these examples, you have the decompositions that release water. And there's also a lovely model material. Brontë, in his PhD thesis at École Normale Supérieure in Paris, looked at a lot of experiments on gypsum. I was a reader of that thesis, so I got to know this work well. And gypsum is nice because at temperatures that are achievable and not horribly dangerous in the lab, it begins to dehydrate, and then a second dehydration occurs at other temperatures that are not a lot higher. So it's a wonderful model material for this kind of process. Now, what are the evidences that this actually happens, this thermal decomposition? Well, one directly from the field, there's a region around the Chi-Chi rupture zone, the Taiwan rupture of 1999, which is simply depleted of carbides, whereas the adjoining gouge does have a concentration of carbide particles in it. So that's a suggestion that a thermal decomposition took them out of action here. And also in experiments, which when the time I made this slide, there wasn't that much around, but Brontë's PhD thesis added several more, but in particular, thermal decomposition of calcites were observed in high velocity friction tests, and I'm going to show you some information from one of those tests. This was done on a marble. In fact, that was one of the experimental specimens of that marble. So it's a cluttered slide, but let's just focus on this. What these investigators looked at is the friction coefficient at fairly large amounts of slip once things got hot enough to activate these decomposition processes. So here are friction coefficients dependent on the slip rate of the test. Those are different for the different curves here. At a fixed normal stress, not as large as we would like, but healthy. And what you see is that as the slip rate goes up, the friction coefficient goes way down in the range where we activate this thermal decomposition. Another way of looking at the effect is here. Here's a conventional kind of plot of shear strength versus normal stress. And the beginning of slip is completely consistent with normal static friction. But once you look at what's going on when you're way out here at large slips and you've heavily dehydrated or decomposed the material, you get extremely low friction. So again, these are thermal decomposition processes that lead to thermal pressurization. Now, there's something else floating around in the literature, and I'm not going to have time to dwell on this, but in some of the nanoparticle experiments, I'm trying to remain neutral on that. I don't think the physics is at all clear, but it suggested that thermal decomposition also creates very, very fine solid product phase particles. And some have argued that just shearing those extremely small particles brings in some additional weakening, but the physics has not been identified. I think to the extent that the data really does show that, there's some possibility that what we're seeing is this. When you suddenly create a lot of nanoscale sized particles, you create a gigantic amount of surface area per volume. That means that anything that would absorb on a surface, like moisture from water in the air, and this room air is plenty moist enough to deliver a lot of water to any freshly exposed mineral surfaces, you would have a gigantic amount of water trapped on the particle surfaces. So if you start to shear this aggregate, the water would go into the pore space, but the pore space is very small because they're nanoscale range particles. They're very fine particles, so it's a very impermeable pore space. So we're back to thermal pressurization. So that's my suspicion as what might be an underlying physics, but that's certainly debatable if you talk to colleagues in the field, and I'll just leave it as unclear. Okay. Well, this just reminds us that, of course, if this whole laundry list of earlier possibilities fail, then you will finally melt, and we do sometimes see melt at large slip of deep events when that rock is seen at the surface. Okay. This is more on thermal decomposition, so I'll just, what changes in our mathematical description when we have thermal decomposition? And basically, if C tells you the amount of a reaction, so C runs from 0 to 1, and it's an Arrhenius-like temperature dependence of the reaction. As the reaction goes on, you reduce the rise of temperature, and it's effectively a latent heat effect. The frictional work delivers energy to latent heat of the transformation rather than to rise in temperature of the aggregate. Also, as you let the reaction proceed, the reaction is, after all, generating this solid product phase and very highly pressurized fluid phase that doesn't have enough room to fit in the region that the constituents used to occupy. So that makes the pressure go up. So these are two parameters, and those parameters can be estimated roughly for different kinds of rocks that are subject to such decompositions. And from that, we can make elementary estimates of what we think thicknesses in microns of localized zones might be, and also representative temperatures when you would expect to see this decomposition. They're all less than the melting temperatures of the corresponding rocks. And a couple of things can be done here. First, linear stability analysis. You get the same results that I already showed you for thermal pressurization if you don't activate the reaction. If you fully activate it, then you get similar like formulas, but that involve these parameters of the thermal decompositions, and you get a reduction of order of a factor of 2 in thickness of the localized zone. And in between, there's a very complicated mess that depends on how big the reaction rate constant is and the activation energy and so forth. But these two extremes are very easy to characterize and think about. Now, these are some nonlinear simulations of shear of our gouge layer, but of a thermally decomposing material. So this shows the case where strain rate is being contoured. So here's the accumulated slip from that velocity of 1 meter a second that's applied at the edges of the layer. You see everything localizes within the layer, and all of the significant strain rates are here. So shear localizes. You can also see here the reaction rate, and you can see that the reaction goes strong here, but then it begins to attenuate a bit. And what happens as it attenuates is well illustrated on a couple slides here. So this is another case where we're looking at strain rates and hence localization and reaction rates. But ultimately, you run into cases where you have completely depleted the product that you have there to react. When that happens, of course, you can no longer sustain this mechanism. And what the system does, at least in our simulations, is it finds some neighboring place to mess with. So this shows that the zone of localized shearing would shift in place just because the region that was shearing up here has become depleted, but some neighboring region got hot enough to take over. And we can kind of see that here, where you see contours of the decomposition reaction rate. It peters out on one side, but manages to continue vigorously in the as yet unreacted material on the other side. And if you now take those strain rates and integrate them in time, you get a very interesting prediction which has some resonance both with field results and nature. If you look at the strain accumulation, it suggests that in some cases you will see a laminated distribution of strain as a result of this depletion of the reactant and migration across the zone. And it may be editorializing too much, but there's some hint of this in the experiment. This is a specimen, and the cracks, at least we were told by the person who did it, Tom Mitchell of Liverpool, that the cracks came later when the thing was taken out of the apparatus. But you can see these white markings, which are evidence of extreme decomposition. And you can see that this stuff here shows signs of strain, but it's less decomposed. So this may be an example of a migrating thermal decomposition zone. Okay, now I guess my time is almost up, so I'm going to just skip through some highlights here. But what does all this mean for earthquake dynamics? Because so far I've tried to explain to you how it is that faults can become really weak during shear and how localized the shear can be. But for earthquake dynamics, what we have tried to do is the following. We've tried the problem of two elastic half spaces which join along a fault. Along the fault, we assume that the kinds of thermal weakening processes I've described to you go on. In particular, we look at thermal pressurization of native pore fluid. We solve differential equations in the direction normal to the fault, which describe the transfer of pore fluid pressure and heat in that zone. And because diffusivities are of the order of millimeters squared per second and rupture speeds are of order of kilometers per second, the region affected by these transport differential equations is a thin strip, a very thin strip about the fault. So locally, we can use a 1D model of that. but we use a fuller model of the surrounding elastic continuum and superpose a large number of series in the sense of a Fourier series of exact solutions of the elastodynamic equations in the two half spaces. So that's the numerical method in a nutshell. It gets a velocity weakening friction put into it, which is based on parameters hinted at by data on granite in the studies of Tullis et al. And as I said, we solve these transport equations for pore pressure and temperature. And here they're put in not on a plane, but over a region that has a Gaussian shape with a width W. So W, when you see it, is that width. We think we know at least the general ballpark of some of the parameters here. And this summarizes what we found in all of the calculations of spontaneous ruptures, which were nucleated artificially. Because of that artificial nucleation, you'll see some artifacts in a moment that I'll point out to you. But they were nucleated. The ruptures propagate spontaneously on a surface whose resistance to shear is set by these thermal weakening processes that we are modeling at each grid point, if you like, along the rupture. This is done for rock properties where the static friction coefficient, which would correspond to a ratio of shear to effective normal stress, which is way out here at 0.8. So we are getting ruptures to propagate at much lower stresses, and we don't know a lot about properties, so we have a big range here of what might be reasonable numbers to put in for diffusivities and the like, so that's why there's a range here. But what we see that is in different parts of this diagram, we can get ruptures that just propagate indefinitely, and they're the red dots and the yellow squares. And then finally, if we make the stress too low, we get arrested pulses. But the important thing is this: the range of stresses that will a rupture, once nucleated, to grow indefinitely is a range of stress which is far, far below the static friction level. Now, the significance of that is it tells us the way the community has been thinking about the stresses at which faults operate might just simply be wrong. People have traditionally thought, well, what's the static friction coefficient of the fault material? That must be the stress I need to make an earthquake. Well, if you've studied any fracture mechanics, you know that you don't think that a glass rod breaks at the theoretical strength of perfect glass. You rather think it breaks at a strength determined by a little defect that makes a stress concentration and starts a rupture. So the way we now think on the basis of this work about large earthquakes is the stress level at which a mature fault, a well-slid fault, should be operating at is the stress level which gives the following property, that if I, through some defect in the system, nucleate a small earthquake, and small earthquakes happen all the time. If I nucleate a small earthquake, then there will be a certain stress level for which that earthquake can grow indefinitely, at least in the mathematical model, indefinitely, in nature, large distances. And that's what these stresses correspond to. So, and just to make clear what crack-like, pulse-like, etc. means, here's an example of a rupture that was started. These were calculations that required a very big parallel computer, a blue gene system with over 100 processors, so it was expensive to run them out very far. But the point is that we got classical crack-like ruptures. You're looking at successive times of the distribution of slip on a fault, and the pulse in the middle is because of the artificial nucleation method, which just overstressed a thin strip near the center. So that's what happened if you have stresses out in this region here. If you go slightly lower in stress, you get into the range of those yellow squares, which are pulse-like ruptures. So these are so-called self-healing pulses As the rupture propagates, the slip just locks into place, and then slip no longer continues. It stays slipped but locked. So that's a pulse mode. And finally, if you go to lower stresses, you don't have enough oomph in the loading to make the rupture propagate, and you get something that quickly dies. So either of these growing pulse or crack-like are ruptures that could propagate indefinitely once nucleated, and the stress levels for that are, again, I emphasize, far, far lower than the static friction coefficient of the fault. So that emphasizes that range. Okay, now again, apologies for skipping. There just a variety of slides I don't want to go over, but in nature, it's been established for some years that most earthquakes are of the self-healing pulse mode. So we're very happy when our simulations predict that, and it's rather rare that a big earthquake looks more like a classical crack than a self-healing pulse. This just says the stress drops are a simple calculations predictor in the range of what seismologists infer. Sorry to jump over that. And the only good test we have is there was a program to drill into the San Andreas fault. As part of that, a pilot borehole had stress measurements made in it. Those stress measurements were consistent with high friction coefficients in the range of 0.6 to 1.0 in the adjoining crust. However, when you resolve the principal stresses determined in the borehole onto the San Andreas fault, you see that the ratio of shear to normal stress is quite low, getting down towards 0.2 at the deepest measurements, though of course this is not very deep, just 2 kilometers down. So the significance of that is the region where these stresses were measured is the same region which underwent an earthquake a few years later that ruptured a zone of about 20 kilometers along the fault. So we know that a big earthquake occurred at a part of the fault which, at least based on shallow mechanisms, is under low stress. So that's as far as we are as far as confirming all of this. I won't go in detail over this summary because I wanted to say just a few words about something else. And this is not my own work, but it's the work of Nadia Lapusta, a former student of mine, and Hiro Noda, also a former student, but independent of me, stuff they did at Caltech, where both of them were at the time. Nadia still is, and Hiro is in Japan. But they looked at two of the earthquakes I've discussed, the Chi-Chi earthquake in Taiwan, and also the great devastating March 2011 Tohoku earthquake off of Japan, the one that launched the massive tsunami. And what they point out is that in the south, the fault zone material is what we call velocity weakening, very brittle, easy to nucleate earthquakes, but it's also rather permeable compared to what's in the north, which is rate strengthening, so it's hard to nucleate an earthquake, but it's less permeable, so it's susceptible to thermal pressurization, which is one of our dynamic weakening mechanisms. And a sign of that difference in property directly in the seismology is when you look at recorded seismograms, those radiated from when the rupture was in the more southern part have a lot of high frequency content compared to those radiated when the rupture was in the more northern part. But the amount of slip contoured here is much greater in the north than in the south. So that's a puzzle, but it's like the, well, and they tried to study that kind of thing through simulations of earthquakes on a patch that was loaded in shear with a southern patch easy to nucleate earthquakes on, but not susceptible to dynamic weakening, a northern patch hard to nucleate, but susceptible to dynamic weakening by thermal pressurization. And what they got is something that resonated with the history both in Taiwan as well as in Japan for the Tohoku earthquake. lots of little earthquakes, well, big enough if you live there, but small compared to the biggest possible earthquakes. And then occasionally these smaller earthquakes grow into a massive earthquake that is able to rupture the thermally pressurized zone. And it can be argued the same thing happened in the great Japanese earthquake of March 2011. Previous earthquakes in Japan scattered along the zones indicated by the contours here, but the big earthquake ruptured the stuff up here, which had been thought stuff that would never participate in a major earthquake. And once again, what we think this is due to is just differences in properties. It has been confirmed that the high frequency radiation again comes from down here and not from up here, but the biggest slips getting up to of order 50 meters, which is a gigantic slip in an earthquake, half a football field, they occurred out in this more shallow part of the subduction zone. I think I have another picture there, but I won't belabor the point. So just to summarize, the static friction coefficient of a fault is much larger than what it sustains during a seismic event. There are documented weakening and localization processes, flash heating, thermal pressurization, in situ plus decomposition product related. There is a still mysterious nanoparticle weakening, and if these all don't keep the temperatures from reaching melting, finally you melt. So there's all sorts of weakening processes. The static strength is simply an unreliable predictor of pre-earthquake stress on major faults that are well slipped in the sense of undergone many previous earthquakes. But they may operate at or near a level at which a small event, once nucleated, propagates indefinitely. Why does this not apply to less mature faults? Well, less mature faults have much rougher surfaces, and we think it's because the roughness means you always have to deform the sidewall significantly to slip the fault. So they tend to operate at higher stresses. And finally, the very important result, which fooled the Japanese in their planning for seismic safety for their nuclear plants, the fact that a segment is creeping does not preclude it from having a large co-seismic slip, and precisely that happened in the northern part of the Chichi earthquake and in the part of the Japanese Tohoku earthquake closer, further from land and out closer to the trench. Okay, thank you very much.